We're given the differential equation governing a circuit. The input is u of t and the output is this parameter v of t. We want to find v of t as t goes to infinity. That means that we're looking for the particular solution. So the solution is going to have the same form as the forcing function. In this case, the forcing function is a sinusoid, 3 cosine of 2t minus 20 degrees. That means that the form of the solution, v of t, is going to be some number, say v sub m, times cosine of 2t, has to have the same frequency as the input since they have the same form, plus some phase angle, theta v, and all we need to do is find v sub m and theta v. I can find the particular solution by plugging this in for u of t, this in for v of t, taking the derivative of v of t and plugging it in there, and then solving for these unknowns, v sub m and theta v. However, that approach is a little bit tedious if you use cosines and sines, because you end up with a bunch of trigonometric identities and the algebra gets messy. The algebra becomes easier if we pretend that the input is a complex exponential. So u of t is some phasor u e to the j2t, where that phasor is 3 e to the j 20 degrees with a negative sign, e to the j2t, so that the actual input is the real part of this complex exponential. Now, if we pretend that this is u of t, then the form of v of t is going to be some phasor v e to the j2t. It has the same form as this input, and dv by dt will be v times j2 times e to the j2t. Complex exponentials are easy to differentiate. Now I can plug this in and this into our original differential equation, plug this in for the input, and our differential equation becomes 3 times dv by dt, which is the phasor v times j2 e to the j2t, plus 6 times v, which is the phasor v e to the j2t, and that's equal to 4 times the input, which is 3 e to the minus j20 degrees e to the j2t. Now something very wonderful happens. All of the e to the j2t's cancel out. We're left with something that's no longer a function of time. It's just an algebraic expression with complex coefficients. So multiplying out, this becomes j6 times v plus 6 times v is equal to 12 e to the minus j20 degrees, and our problem is now just a complex arithmetic problem. So v, if I divide out this j6 plus 6, is equal to 12 e to the minus j20 degrees over j6 plus 6. Division's easier in polar form, so I'm going to convert the denominator to polar form. 12 e to the minus j20 degrees over 6 root 2 e to the j 45 degrees. So v as a phasor is going to be 12 over 6 is 2 over the square root of 2, and e to the minus j20 minus 45 is minus j 65 degrees. So there's our phasor representation for the output. This gives the magnitude and the phase angle in this expression up here. So v of t, as t goes to infinity, is equal to 2 over root 2 cosine of 2t. The frequency is the same as the input's frequency, minus 65 degrees. Now we want to sketch a phasor diagram showing the input and the output phasors. In phasor form, u of t was u e to the j2t, which was 3 e to the minus j20 degrees e to the j2t. So here's the phasor representing the magnitude and the phase of the input. And we found that v of t was 2 over root 2 e to the minus j 65 degrees e to the j2t. So this is the phasor form for the input. So sketching that on a real imaginary axis, u has a magnitude of 3 and a phase and an angle of minus 20 degrees. So this is u. It's got a magnitude of 3. V has a magnitude of 2 over root 2 and a phase angle of 65 degrees. So 2 over root 2. This is V as a phasor, and the phase difference between them is 45 degrees.